Welcome friends to this new lecture of soil science and technology, and in this week 6, and today we will try to finish the electrical diffuse double layer theories, and we will move ahead and go to our next topic, that is adsorption isotherms, and then we will try to finish that. So, in the last lecture we have covered the basics of electrical double layer, electrical double layer, that is diffuse double layer theories and its properties, its assumptions, and I talked about different diffuse double layer theories like Helmholtz double layer, like Gouy-Chapman layer, and then Helmholtz double layer, Gouy-Chapman layer, then Stern layer, and then we talked about what is the basic, what are the differences between these three theories, and we talked about it as their assumptions, and then we talked about the practical implications of diffuse double layer and its thickness. So, if you remember, in the last lecture we have talked about that how the thickness of the diffuse double layer is influenced by the valency of the ions as well as the concentration of the electrolytes. And if you remember that opposite to repulsive forces, the clay suspension is also subjected to the interparticle attraction, we call it van der Waals force, and the van der Waals attraction is only effective at very close distance, and which is less than 20 angstrom, and it decreases it decreases rapidly when the interparticle distance goes beyond 20 angstrom, and the interparticle distance is very important, and the repulsion will dominate at low electrolyte concentration, and the clay particles are shielded by relatively thick double layers, and decreasing the possibility of mutual approach. And remember that at high electrolyte concentration the chances of close approach are made possible by compression of the double layers, and in this condition van der Waals attraction may overcome the repulsive forces, and coagulation and flocculation of the clay particles occurs rapidly. And I have told you that this coagulation or flocculation is important soil as far as the soil physical property is concerned, because it helps in aggregation as as opposed to the dispersion of the clay. And dispersion basically occurs due to the due to thick diffuse double layer, and when the soil is dispersed it creates the unfavorable physical and as well as different other properties for soil for the growth and germination of the crops. So, let us move ahead and go to our next slide and see what is zeta potential. Now, when a colloidal suspension is placed in an electrical field, remember that the colloidal particles move in one direction and towards the positive pole, we know that because they are negatively charged, and the countercurrents move in another direction towards the negative pole, and the electric potential develops at the solid liquid interface is called zeta potential. And this zeta potential basically the site of the zeta potential is basically is the shearing plane or slipping plane between the bulk liquid and the envelope of water moving with the particle. So, if we consider this is a particle and there is an envelope of water, you can see, which is surrounding the soil particle. The slipping plane is basically the plane which is which occurs at the at the juncture of this bulk solution. Here is the bulk solution and here is the envelope of water. So, here at the junction of the bulk solution and at the with the outer boundary of the liquid film or envelope, this is called the slipping plane, and this slipping plane is the place where the zeta potential occurs. And remember that because the position of the shearing plane is unknown, and the the zeta potential represents the electric potential at an unknown distance from the colloid surface. So, you can see here the zeta potential develops at the slipping plane, and again the slipping plane is the juncture between the outer boundary of the liquid envelope surrounding an particle and the surrounding bulk solution. So, let us move ahead and see what are the other features of zeta potential. Now, zeta potential influenced by the high electrolyte concentration, as you remember that when there high electrolyte concentration, the thickness of the diffuse double layer decreases. At the same time, due to the reduced thickness of the diffuse double layer, also zeta potential also decreases. So, high electrolyte concentration or high valency of anions also decreases the zeta potential, and isoelectric point is the point where zeta potential is critical. It is value of 0, and below the isoelectric point, the clay particle cannot present as disperse in the medium, and they try to flocculate and coagulate. And in other words, isoelectric point is the pH at which the total surface charge is 0, that is so this is called the isoelectric point. Now, the isoelectric point at the critical level, below the isoelectric point, the zeta potential reaches a certain value where the clay particles cannot remain further into the solution and they coagulate, and the zeta potential depends on the surface potential of the clay particles, and it is determined from the electrophoretic mobility of the suspension using the following formula, where V equal to where V equal to d z e by 4 eta and pi, and where V e is the electrokinetic velocity, d e is the dielectric constant, E is the applied electromotive force, and eta is the viscosity of the fluid. So, by using this formula we can calculate the zeta potential. So, also one important thing that you can see here, there are two electrolyte, one electrolyte is given here in low concentration, another is in a high concentration. So, when there is a high concentration of the electrolyte, obviously the zeta potential decreases. So, high electrolyte concentration always decreases the zeta potential and helps in coagulation of the clay particles. So, practical implication of the zeta potential: flocculation or coagulation occurs once zeta potential is below the critical value. This critical value is called the isoelectric point, and the greater the zeta potential, the more stable the suspension. The particle tends to repel each other, hence prohibiting the natural tendency to aggregate, and this repulsion and stable suspension is not helpful for the growth of the plant, because it creates the unfavorable soil physical condition. So, we have finished the diffuse double layer theories. Obviously, you can follow these two standard books. One is The Nature and Properties of Soil by Niles C. Brady and Ray R. Will, and The Principle of Soil Chemistry by Kim H. Tan, 4th edition, and you will have more more detailed idea about this diffuse double layer while you read these two books in details. So, guys, let us move forward and start a new topic, that is adsorption isotherms. Now, adsorption isotherms is basically deals with the adsorption process. Now, we will cover this following concept: what is adsorption isotherm, and then basic adsorption isotherms, and then types of adsorption isotherms. So, what is adsorption? Adsorption can be divided into physical adsorption or chemical adsorption. The another name of adsorption, physical adsorption, is physisorption, and chemical adsorption is chemisorption. So, in case of adsorption, remember that adsorption is a surface phenomena where the adsorbate is attached on the surface of the adsorbent, and it is a it is a reversible, obviously, as you can see here. An adsorbent is the material on which surface the adsorption occurs, and adsorbate is the material which get adsorbed. So, and also there is a bulk solution. So, this this shows in a nutshell about the adsorption process, and the opposite of adsorption is desorption. Remember that adsorption again is a surface phenomena. It is whereas absorption, which is AB, is a internal, which is not surface phenomena, which is an internal phenomena, and the opposite of adsorption is called desorption. And obviously, in case of adsorption process, adsorbate and adsorbent takes part in basically reacts with each other. So, what is the adsorption isotherm? Obviously, the process of adsorption is usually studied through graphs known as the adsorption isotherms, and it is graph between the amount of adsorbate x and adsorbed on the surface of adsorbent m, where in this case in our case, in case of soil science, we will consider this adsorbent as soil and at a constant pressure and temperature. And two methods are available. So, adsorption isotherm is basically again showing the is the relationship between the amount of adsorbate adsorbed on the surface of the adsorbent and at a constant pressure and temperature. And two methods are available in the use of adsorption isotherms to study the behavior of the adsorption reaction. First is the identification of the shape and curvature of the adsorption isotherms, we will see in details, and finally, the statistical formulation of adsorption isotherms. And the statistical formulation of adsorption isotherms are also called statistical models. So, we will discuss them in a while. So, let us first start with the shape and curvature of different adsorption isotherms. Now, identification of shape and curvature of adsorption isotherms is basically focused on four basic types of adsorption isotherms. First of all, S type, and then L type, then C type and H type. And remember that these shape and curvature are used to identify the nature of adsorption of solids from aqueous solution. So, in this case here the adsorbent is basically if you remember the difference between the adsorbent and adsorbate, in our case the adsorbent is soil and adsorbate is a particular molecule which is getting adsorbed on the adsorbent from the solution or soil solution. So, here using this shape and curvature of the adsorption isotherms, we use to identify the nature and adsorption of solutes from aqueous solution. So, solids is basically adsorbent. No, the solid is again in our case here the adsorbent is basically soil and adsorbate is basically solute, and here is the solution. I hope that now it is clear. So, let us move ahead and see what is S type. Now, S type is represent the adsorption reaction where the solid has a high affinity for the solvent. So, you can see this shows the relationship between equilibrium concentration and amount adsorbed. So, you can see there is an S shape curve, and this S shape curve basically denote the solid has a high affinity for the solvent. And secondly, there is an L type adsorption isotherm. This L type suggests that solid has a high affinity for the solute. So, in case of S type, the solute the solid has a high affinity for the solid has a high affinity for the solvent. However, in case of L type, the solute has a high affinity for the solute. So, this is an S type and this is again the L type. So, both S type and L type adsorption curves are considered to predict similar things as the Langmuir adsorption isotherm. We will cover the Langmuir adsorption isotherm when we will discuss about the different statistical models of adsorption isotherms later on. But just remember that these S type and L type adsorption curves are considered to predict similar things as Langmuir adsorption isotherm. So, again S type when the solid has high affinity for the solvent, and L type when the solid has high affinity for the solute. So, what is C type? Now, C type curve is also known as the constant partition isotherm. Now, you can see there is a straight line between the equilibrium concentration and amount adsorbed. So, the C type curve is also known as the constant partition isotherm, and the adsorption process is characterized by a constant partitioning of solute between the solution and the adsorbent. And remember that according to Weber, scientist, this type of adsorption is common when new adsorption site become available as the solute is adsorbed from the solution. So again, this S type and L type we already covered. Now C type is called the constant partition isotherms, and the adsorption process here in case of C type is basically characterized by a constant partitioning of the solute between the solution and the adsorbent, or in our case it is soil. Finally, the H type adsorption isotherm. Now, the H type curve, also known as the high affinity curve, represents the adsorption reaction when the solute has a high affinity for the solid. Here remember that solute has a high affinity for the solute. In case of S type, solid has a high affinity for the solvent. In case of L type, solid has a high affinity for the solute. However, in case of H type, the solute has a high affinity for the solid. Now, this type of curve is considered a special type of L curve. Obviously, it is a modification of the L type curve. And in dilute solution, the solute is often completely adsorbed and no measurable amount is left into the solution. So, it basically takes this type of form in case of H type. So, we covered the basic curvature and basic shape of adsorption isotherms with S type, L type, C type and H type. Let us see what are the different statistical formulation of adsorption isotherms, or in other words what are the different statistical models of adsorption isotherms. So, 4 major types of equation have been formulated and are used today to describe the adsorption process. These 4 equations or models are the most common forms of adsorption isotherms which scientists use nowadays. We call it first of all the Freundlich equation and or the Freundlich adsorption isotherm. Second is the Langmuir equation. Third is the BET equation. BET comes from 3 scientists' name, that is Brunner, Emmett and Taylor equation, and finally the Gibbs equation. So, we will cover them one by one. So, let us start with the Freundlich equation. Now, in case of Freundlich equation, the adsorption isotherm in many dilute solution now famous under the name of the Freundlich equation, and is conventionally we write this Freundlich equation as x over m equal to Kc to the power 1 by n, where this x is basically the amount of material adsorbed, m is the amount of adsorbent, in our case it is soil, c is the concentration of the equilibrium solution, and K is the Freundlich adsorption Freundlich adsorption constant, and N, or in other words 1 by N is basically the Freundlich exponent. The Freundlich equation obviously has no theoretical foundation, it is purely empirical in nature, remember that. So, we have seen the basic form of Freundlich equation. Let us move ahead and see what are the physical interpretation. Now, remember that the value of 1 by n, or in other words the Freundlich exponent, is usually between 0.2 to 0.7, and for many pesticide at dilute concentration 1 by n equals to 1. So, however, if 1 by n equals to 1, the equation becomes a linear equation, because x by m equal to Kc, we had the power 1 by n equals to 1. So, the curve according to the equation is usually parabolic, which is exponential, and exhibit the following characteristic features. First of all, there is no single point indicating the process is completed, and there is no region of discontinuity. So, these two are important assumptions. So, again the Freundlich adsorption isotherms, when the Freundlich adsorption Freundlich exponent, that is 1 by n becomes 1, it becomes a linear equation, that is x by m equal to Kc. However, the curve according to the equation is usually parabolic, exponential in nature, and exhibits the following two assumption characteristic features. But so, by replacing the concentration C for pressure P, obviously the Freundlich equation can also be used to describe adsorption of gases by the solids. So, we just have to replace the C by this pressure P. So, basically it will also it will be also applicable for the adsorption of the gases by the solid. So, adsorption of the gases by solid also follows the Freundlich equation. So, let us move ahead and see what is Langmuir equation. Now, another method of statistical formulation of adsorption reaction is given by Langmuir in 1918, and the Langmuir equation, originally derived for the adsorption of gases by solids, is formulated as follows. Obviously, theta equal to Bp by 1 plus Bp, where theta is the amount of gas adsorbed per unit area, B is the constant related to the free energy of adsorption, and obviously P equals to equilibrium gas pressure. So, basically it was applied, originally it was applied for the adsorption of gases by the solid. However, we can modify it for in case of solid, in case of solid interaction also, adsorption also. So, for adsorption of solids into the solution, P can be replaced by C, which is equilibrium concentration of solute in the solution, and the equation assumes the following formula, where x by m, just like the Langmuir equation, K1C by 1 plus K2C. And here remember that this is the basic form of the Langmuir equation. However, the x is the, obviously the similarly just like the Langmuir equation, x is the amount absorbed, m is the amount of adsorbent, and K1 and K2 are the constant, and C is the concentration of the equilibrium solution. This far, these are fine. So, remember that the differences of the Langmuir from the Freundlich equation is that at very high concentration, the value of K2C, this term K2C in equation reaches such a high value that the factor 1 can be neglected. So, we know that x by m equal to K1C plus 1 by K2C. So, when the C is very high, basically what happens, this 1 we can neglect it. So, basically the equation becomes K1C by K2C. So, obviously is become x by m equal to K1 by K2. So, this formula shows that that x by m becomes constant at high concentration. So, in other words, at high value of C, the surface of the adsorbent becomes saturated and adsorption reaches a maximum. So, this is one implication of this Langmuir equation. However, on the other hand, at a very low concentration, the value of K2C becomes so low that compared to the factor 1, that it can be neglected. So, then equation turns into, obviously we know that x by m equal to K1C plus 1 by K2C. So, here it will the value of K2C becomes so low. So, the factor the K2C can be neglected. So, basically it will be K1C. So, the equation change into x by m equal to K1C. So, the Langmuir equation is useful, remember, for monolayer adsorption, which is generally in case of chemisorption or chemical adsorption, and adsorption for the solution and physical adsorption of the gases. So, now you have you have idea about the Langmuir equation and Freundlich equation. So, let us go ahead and see what is BET adsorption isotherm. Now, BET theory put forward by these three scientists, Brunner, Emmett and Taylor, who explained that multilayer formation is the true picture of the physical adsorption. Now, one of the basic assumption of Langmuir adsorption isotherm was that adsorption is a monolayer in nature. However, these BET assume that there are multilayer adsorption, multilayer adsorption is possible. So, for multilayer adsorption, the use of BET equation is suggested, and in this respect, the BET equation is considered as extension of the Langmuir equation. It is considered as an extension of the Langmuir equation, and the BET equation, you can see this is the formula of the BET equation. So, let us go ahead and see what are the meaning of these terms. So, in this BT equation expression, P is the equilibrium vapor pressure, P0 is the saturation vapor pressure, V is the volume of gas adsorbed, Vm is the volume of gas adsorbed when the solid is converted with a monolayer, and C is the constant related to the heat of adsorption. So, this is basically the the equation of BT, of the BT isotherm, and these are the meaning of the individual component. Now, what are the assumption? Now, the assumption of BT equation is the heat of adsorption in the second, third and nth layer are the same as the heat of adsorption in the monolayer, that is heats of liquefaction or condensation of the gas. And secondly, if the adsorption takes place on a free surface, then at P0, that is saturation pressure of the gas, an infinite number of the layers can be built up on the adsorbent. So, these two are assumption, basic assumption of the BT equation. So, what are the advantages of the BT equation? Obviously, it describes the multilayer adsorption and it yields the volume of gas required for the formation of the monolayer, and it can be used to calculate the surface area of the soil by multiplying Vm with the cross sectional area of the adsorbent molecule. So, these are the three advantages of this BT equation. Finally, the Gibbs equation. The Gibbs equation describes the processes in relation to the surface tension, and it is formulated as follows, where is tau equal to minus A over RT and then d gamma by dA subscript T, where tau is the surface concentration of adsorbed material in moles per square centimeter, and A is the activity of the solute in moles, and R is the gas constant, that. T is the absolute temperature in Kelvin, and the gamma is the surface tension in dynes per centimeter. So, this Gibbs equation takes this form, and the solute is adsorbed on the surface of the adsorbent if d gamma by dA is negative. So, if you consider, if you remember, this is a negative term. So, if this d gamma by dA, which is this term, is negative, so ultimately tau is positive. So, this type of adsorption we call it positive adsorption. When the tau is positive, when the it is called the positive adsorption. So, therefore, positive adsorption occurs when the solid decreases surface tension, remember that. Now, what is negative adsorption? Negative absorption is just opposite. So, when the d gamma by dA is positive or delta gamma by delta is positive, when that means the tau is negative. So, the solute is more concentrated in the bulk solution than in the interface region. So, in this case it is just opposite to the positive adsorption, and the latter it is called that negative adsorption, and in this case solute increases the surface tension. So, in case of positive adsorption, solute decreases the surface tension, in case of negative adsorption, solute increases the surface tension. And the Gibbs equation finds primary application in adsorption at liquid gas interface, obviously, and it is very difficult to use this equation for in adsorption reaction at the solid liquid interface, because it is impossible to measure the surface tension of the solid interface or solid surface. It is easy to measure the surface tension at the liquid surface, however, it is impossible to measure the surface tension at the solid surface. So, that is why the Gibbs equation is applicable for in adsorption at liquid gas interface. So, guys, we have completed these adsorption isotherms and their basic their curvature and the shape and the four statistical models of adsorption isotherms. Adsorption isotherm is a very important when there is a adsorption of solutes from the bulk soil solution to the soil solids or the clay surfaces. So, it is very important. Please read these books again, The Nature and Properties of Soil by Niles C. Brady and this Principle of Soil Chemistry by Kim H. Tan, 4th edition, to get more thorough knowledge of this adsorption process. Obviously, we cannot complete all the physical and chemical physical and chemical forces which are responsible for different types of adsorption. So, I request you to go through these books in more details to learn in details about the different types of adsorption isotherms, but however, I have I hope that you have now got basic idea about the adsorption isotherms. So, we are going to finish this lecture, and in the next lecture we will start from the soil acidity and different other problematic soils. Till then, thank you.